get somebody online to do it.
There we go. It's recording.
There we go.
All right. Well, so you've got a black bar down the right side of your screen.
Yeah, that's just
there you go, done.
That's just your smiling happy faces. Okay. So so what are we actually doing when we want to fit a curve, and why are we going to do it? So generally, what we're actually trying to do when we're fitting a curve to data is we're trying to explain the data. We've got a whole load of numbers, and we want to find something that actually explains them. And we can do this by trying to fit a curve which is comes out of a physical model. So you can imagine that if you have a spectrum and you have a good reason to think that this spectrum arises from a particular behavior, like a black body or a galaxy with a whole bunch of spectral lines or something, then you can have a physical model and you just want to fit a curve that comes from that physical model to your data. Or it might be a mathematical model where you don't actually have any particular view on the physics, but what you want is you want to replace your data with something that is reasonably equivalent, mathematically speaking. So this could just be a curve where you don't actually say, oh, I expect it to be a black body. You just want a curve that fits it. So some examples of this are, one of the most common things that I tend to do is fitting a baseline to a spectrum. You have a spectrum, you may be interested in a spectral emission line, but the spectrum itself has structure in it. It's not a perfect flat thing, but you want to turn it into a perfect flat thing. So you fit what we call a baseline, which is a mathematical curve which explains most of that spectrum. You subtract it off and you get a nice flat baseline, and you're correcting an issue in your instrument. In that case, you have no particular physical model you're trying to fit to. You just say, I just want to get rid of these effects and I don't care what they are. You might, on the other hand, be actually fitting a model to data points where you have your specific data points from your experiment or your observations, and you want to fit the model to say, these data are telling me about this model. Something pretty similar to that is you can fit a physical feature like a black body. I've talked about that, and lots of other things. This is a very general problem. So what you're doing here is you're fitting a whole load of data, which could be, a dozen data points, or it could be 1 million data points, but you're going to fit to those data a curve which is defined by only a few parameters. And those parameters, those few numbers that you fit, are now the things that actually encapsulate your understanding of the data. So you turn your spectrum of maybe 100 data points into a black body curve, which has maybe 2. Or if it's a gray body curve with an emissivity component, it may have 3. So you've got far fewer numbers to deal with. And so this is an essential part of actually deriving information from your data. And technically, this is a process of inference. You're taking your data and you're inferring meaning from it. So this is part of the whole process of inference. And this is I've stolen a couple of things from this book, which I'm planning to use this semester, which is quite good. So once I've finished with it, feel free to grab it from the library. So what's the simplest way to fit a curve? The simplest way to fit a curve is not to fit a curve. It's to fit a straight line. But a straight line is actually just a curve that doesn't curve very much. So in this case, we can take, so I thought, well, what's an example of a straight line? How about the radio FIR correlation, where you take a whole bunch of galaxies and you look at their infrared luminosity, you look at their radio luminosity, you plot them on a big scatter plot, and lo and behold, you get a straightish line. Or at least you get quite a nice straight line with a whole load of scatter on it. And so in this case, this is telling you something about the universe. This is telling you that the radio and infrared luminosity go together in quite a controlled way. So how would you actually go about fitting that line? What's better than just plotting everything and grabbing your ruler and drawing a line and going, oh, that looks nice? Well, the simplest thing you can do is called simple linear regression. It uses least squares fitting, where what we say is we want to take all of the the residuals, all of the discrepancies between the model and the data, square them, add them all up, and find the model that minimizes that least squares residual. We're going to fit a straight line to the data, and it turns out in simple linear regression, you can do it analytically. You don't need a computer unless you've got a lot of data points. You can actually go straight from the data to the best fit, and you can get a correlation coefficient out of that and all sorts of good stuff. So what you're doing is you're fitting a straight line where your data is a y, is an xy data set, and you're fitting a straight line y equals a plus bx. So you can see that you're doing something like that. And least squares fitting, this is one of the ones I stole from the book. So what you're actually doing when you do least squares fitting, if you're a sort of graphical interpretation of this, is that if you look at the discrepancies in y, and then you kind of draw that little hatch square around them, then what you're doing is you're adjusting that line, you're adjusting that straight line until the gray squares, the total of the gray squares is the smallest you can get. So if you wiggle that straight line a little bit from where it is, then some of them will get a little bit smaller, some of them will get a lot bigger. And so the total will actually get worse. So that straight line that we've got there is actually minimizing the least square residual. And this is the basic thing we're trying to do. You may already all know this, but it's an important thing to keep clear, because least squares fitting is basically the most important thing we do in curve fitting for almost anything you do. Okay, so linear regression is great because it's analytical and gives you an answer. And the bad news is that it is only valid when your errors in one of your kind of data axes are basically negligible and you're fitting a straight line. This almost never happens. So for example, that radio FIR correlation isn't really a simple linear regression because your errors in infrared are not that negligible, nor are your radio ones. So you're not really able to do a proper simple linear regression. So that's bad news. Not so bad is that you can actually use non-simple linear regression, non-simple meaning you can't just write down the answer, but you can use it if you don't have a straight line, but if your model is linear in your model parameters. So that means the A and the B in the y equals a plus bx, the A and the B are your model parameters. And if your model is linear in those, you can use linear regression, but it's not simple linear regression, so you'll need a computer. So this is the good news, which is that you don't actually need to do it yourself, because every data analysis package, every data language will do this for you. And things like LM in R, lots of stuff in Skippy and Python, and all of the specialist software like Myriad that you use regularly will have packages that do this. So much for fitting a straight line. What about fitting a not straight line? So the next step up in complexity would be a polynomial, where what the curve we're fitting, instead of y equals a plus bx, is y equals a plus bx plus cx squared plus dx cubed plus ex to the fourth plus fx to the fifth plus, and so on, until you get bored or it stops being a good idea. Here's another thing I lifted from the book, where you've got a whole bunch of data, and here are two possible fits to it. The first fit you could opt for is a second order polynomial. That's the solid line. And that's basically just y equals a plus bx plus cx squared. So there are three parameters in there, a, b, and c. And you can see that the x squared is probably going to be a bit negative. And so the whole thing is this kind of inverted parabola. And it's not a bad fit. Or you could go for the dotted line, which is a great fit. And that is a fifth order polynomial. And and as you can see, it pretty much passes through every data point. So there we're getting up to something x to the fifth in our, so we're going to have y equals a plus bx plus cx squared plus dx cubed plus ex to the fourth plus fx to the fifth. And that's going to be the model that we're fitting. The problem is that actually it's not clear that what we're doing there is meaningful. What we're doing is probably overfitting the data, because you got 6 free parameters. 6 degrees of freedom. And if you count them up, you've got 7 data points. So at that point, you're actually not explaining much about your data because you're taking 7 numbers and you're inferring a model that uses 6 numbers out of it. So you're not really, if you had a 7th order polynomial, you should be able to get it going through every single data point there. So this is, as you increase the degree of your polynomial fit, you're getting less and less convincing, even though your fit is getting better. And so in machine learning terms, this is called overfitting. And in scientific terms, it's called bad science. And so you have to be careful with your polynomial fits. It's very easy to just increase your polynomial fits until everything looks lovely, but you can go a little too far. Here's not precisely a cautionary tale, but an example of where you have to be quite careful. So this was a couple of years ago. Jane Greaves and collaborators detected phosphine in the atmosphere of Venus. This is still contested. Nobody's quite sure whether they've got it or not, and the Leiden group basically wrote a very strong rebuttal on this, which makes it look pretty dubious. And as part of it, Jane and co actually fitted out a 12th order polynomial to their spectrum so they could get so they could actually get a good detection of their spectral absorption, which you can see on the left-hand side. Now, the thing is, Jane is not stupid, and she knew perfectly well she was skating on pretty thin ice with a 12th order polynomial. And so in the paper, they actually go into a lot of detail to make sure that they're not fooling themselves with the 12th order polynomial. And in fact, when the Leiden group attacked it, they didn't attack it on the 12th order polynomial, apart from an occasional, really? They attacked it on other grounds. So you can use very high order polynomials, but you really need to be careful and justify what you're doing. My old boss used to say you should never go above linear, and anything else you should just go away and get better data. But he was a little eccentric in that regard. Okay, so curves can get more complicated still. So in this case, these are some fits I did in my thesis a long while ago. And these are sky dips. And it turns out that when you do a sky dip, which means that you point your telescope at the sky and you point it near the zenith, and then you move it down in steps towards the horizon, then what you see is as the air mass increases, the brightness of the sky increases because you're looking through more atmosphere. However, it's not just a straight line. It's quite the simplest possible model that does a reasonable job of reproducing it is this expression at the bottom, and it is not at all linear. You cannot use linear regression on this. It is a completely nonlinear fit, and you've got multiple different variables in there. The parameters that you're fitting are tau, which is the optical depth of the atmosphere, eta tel, which is the efficiency of the telescope, which you don't really know from first principles, you have to measure, and b, which is a kind of efficiency of the filter that you're using to actually take your data. So there are 3 parameters in there, all of which can shift, all of which can need to be fitted. So when you do nonlinear fitting like this, and I'll just actually flip back to say, this is pretty good. We can get a pretty good model fit out of this, but it's non-trivial to do it. And so you're still using least squares though. So the implementation of least squares is very different in that it becomes more complicated, but the basic principle that you still want to minimize the least squares residual between your data and the model is still there. So what we're actually trying to find here when we fit this model is a combination of parameters that defines the curve with the smallest least square residual. Sorry, I should have put minimum in there, I guess. And the problem with this is that you don't have to have a very complicated model before your parameter space becomes very, very large. And you can't just go backwards. So in the linear regression, the simple linear regression problem, we're able to take the data and go back to a model. You can't do that for anything other than simple linear regression. So you have what's called an inverse problem, where it's pretty easy to take a set of parameters, figure out the curve and figure out the residual. It is hard to impossible to take a set of data and then go back directly to the parameters. What you have to do instead is you have to try a whole bunch of possible solutions and pick the one that you like best. And the least squares residual is the tool we use to decide which one we like best. So of course, one option is to simply sample the entire parameter space, compile a list of all the possible models, all the possible residuals, and find the one with the smallest residual. This is a bad idea. If you don't believe me, feel free to try it someday. I once did before I'd learned a bit more about curve fitting, and I gave up after when the computer was just sitting there for a few hours and I needed to go home. It doesn't work. So you have to use numerical techniques which actually allow you to sample the parameter space efficiently. And the simplest one is you find a spot and you go downhill, which means you go toward you start off in one place and you try a few neighboring solutions and you pick the best of those, and so you go to a better spot, and then you try the neighboring ones and you keep going what's called downhill. So what you're going down to a minimum of the least square residual, which is sometimes called downhill simplex and sometimes called amoeba, because it's like a blob that's just sliding downhill until it reaches the bottom. And then you say, that's my best one. You can do Monte Carlo sampling, where instead of trying to find every model, you just take a random sample of the model and you go, well, that's probably going to get me pretty close. The one that I learned how to use in my thesis is called Levenberg-Marquardt, which is kind of this hybrid method that uses a combination of trying to find which way is down, so which way is better from where you are now, but also sampling around it just to make sure that you're actually not kidding yourself about where the minimum is. Levenberg-Marquardt is quite complicated, but very efficient. So it's also, of course, implemented fully in computers, which means you don't actually have to write it yourself. You just have to learn how to pass the relevant parameters to the implementation that you have and get it to do the work for you. So one of the examples I talked about is fitting a physical model. So this is what I'm calling here astrophysically motivated fitting, where instead of just trying to fit a polynomial, so just get something that describes the data, I'm actually going to say, no, I believe I know where these data come from and what they're trying to tell me about. In this case, what I've got is a protostar, M8 East, and we've got wavelengths out in the far infrared. And we expect that this thing should look kind of like a black body, except with a whole bunch of complications thrown in. So we expect that the spectrum should look like a black body. And it's not too far off. So what we're doing here is that instead of just trying to fit anything with our curves as being of a particular form, which is defined by the physics, and then we have a bunch of parameters in there which we can vary. So our parameters, we still have a parameter space, we still have to search it. In this case, the relevant parameters are a radius of the blob. It's a big blob of warm dust. The temperature, 28 Kelvin, a density, a P and Q, which are parameters which talk about how peaky it is, a profile of densities and temperatures, and beta, which tells you about the dust emissivity. So you've got about, and then there's a distance which scales the brightness. So you're actually looking at about 7 parameters in there, and we've got maybe a couple of dozen data points. So it's not overfitted, but you haven't got a lot of room for maneuver there. So pretty much the last thing to go over is so what we've talked about so far is how you get your best fit. How do you fit a curve, which means what is the curve that is the technical best fit to the data. But it's all very nice to get the best fit, but it's also important to ask what range of parameters could give a reasonable fit or an acceptable fit. Because, okay, you get your best fit, but does that mean that if you shift the parameter by 0.01, are you wrong? Is that then what's so wrong that you wouldn't even consider it? Or is it pretty close? And so maybe you could consider it. How do you actually do that? that's quite tricky. And it gives us the idea of the confidence interval. The range of fit parameters that fit your data well enough is your confidence interval. So here's a basic idea of how you do it. This is not precisely the same thing, but it's the same basic idea. And I did this stuff in my thesis before I actually knew how to do confidence intervals properly. So there are some things in here which are a bit iffy, but it gives you the basic idea. What I'm going to try to do here is I've got a mass spectrum with not a lot of points on it, and that's top left. And what I want to do is I want to fit a power law to the slopey bit, not the flat bit on the left, the slopey bit on the right. And I'm going to use a cumulative density function to actually fit that. And I'm going to use a Kolmogorov-Smirnov test to give me the probability that any given cumulative density function is consistent with those data. Don't worry what a Kolmogorov-Smirnov test is unless you end up doing something like this, in which case they're awesome, trust me. So what I did is on the right-hand side, what I'm doing is I'm saying for all of these power laws, so I'm fitting a power law, and it can have any kind of index alpha, from a very shallow one at a low alpha to a very steep one at a high alpha. And I'm just going to try a whole bunch of them and see what is the probability, what is the consistency between my data and a power law that looks like that. And what I find is that it peaks up around 1.6, 1.7. But you can see it's a fairly sharp peak. So if I say the best fit is 1.7, and you ask me, could it be 1? The answer is, not really. Because if you look at alpha of 1, you're getting really low probabilities. So no, it's not 1. If you ask me, could it be 2? It's like, probably not. So already this is kind of giving you the idea that you can get some sense of roughly what your confidence interval is going to look like. But you can do this properly. What I've done so far is extremely hand-waving, and you can do it much better. And what you actually do is you can end up using chi-squared as the measure of at what point your confidence slips from pretty good or good enough to not good enough. Now, you can also do your confidence intervals in a multidimensional parameter space. So what I did before, in the last slide, I only had one dimension, and that was alpha, the slope of my power law. What I'm doing here, this actually goes back to my SkyDip data, which was the nonlinear fit with the telescope efficiency eta, the filter efficiency beta, and the optical depth tau. And what I can do is I can plot something like this idea of something like a chi-squared or a least squared residual over this multidimensional surface. So up on the top, for example, I've got eta against tau. And what I've got then is I've got a surface. The contours are telling me where how much the residual is. And you can see you've got this kind of slightly odd shaped, what you would ideally like is you'd like a beautiful circular minimum, and then in the middle of that would be your best fit. What I've actually got is this elongated ellipse kind of in a diagonal form, which is not really what you're looking for, but it's what we get. And so what you can do is you can see from this that there is a best solution, a best fit, but you can also see how peaky the residual distribution is. If it's a sharp peak, then you've got quite a narrow confidence interval. If it's very broad, then you're going to end up with a broad confidence interval. So if you look at the one middle right, you can see you've got a very sharp confidence interval in tau and a very wobbly confidence interval in B, which is actually good news, because in the case that we're working here, which is the air mass, the SkyDip, all I actually care about is tau. The number I want is tau. B, I don't really care about. It's just a parameter I have to fit. So as long as I get a good tau, I'm happy. So that was pretty good news when I saw that. So there is some actual real maths underneath here. And what we're looking at is the idea of maximum likelihood. So likelihood is not the same as probability, because if you think in traditional probability terms, you can set up a hypothesis, which is, okay, the temperature of the black body is this much, and then you can calculate the probability of getting the data that you see based on that hypothesis. But you can also go backwards on this, and you can calculate the likelihood of a particular temperature giving you the data that you observe. And that means that you can do that for any temperature, which means you can set up a likelihood function, which is in this case, the likelihood of any given temperature. And then all you have to do is find the maximum of that likelihood, and that's your best fit. Not only that, that curvature, the curvature of that likelihood function, what its peak looks like, tells you how big your confidence interval is, which is actually what the Levenberg-Markov algorithm does, and it does it using a covariance matrix, and it gets extremely unpleasant very quickly, which is why you get a computer to do it. Now, maximum likelihood, which is actually what you're doing, anytime you fit a curve using least squares, you are actually doing maximum likelihood, and it's worth mentioning that this is actually the start of Bayesian analysis, because a Bayesian analysis really is maximum likelihood, except that you start bringing in some prejudices about how things work. So, quick summary, fitting a curve. There's a good reason it was up on the list of things you wanted to talk about, because it is how you infer information from data. It's really important. It's very easy to do simple linear regression, but you will almost never get to do a simple linear regression. You can, a linear regression, straight linear regression is not that much harder, and your computer will do it for you, so you don't have to worry about it. Nonlinear regression is a way trickier. Again, your computer will do it for you, but there are many things, it's complicated, lots of things can go wrong, and so you really need to be aware of how it works and what you're doing so that you know whether or not you're screwing up. That was my summary, and sorry for going a little over. I blame the epsilon machines. So, any comments, questions, or anybody wants to tell me I'm wrong?
Yeah, very good. Questions?
Can we have a follow-up where you bring in errors?
You mean errors on your data?
Yes.
Yes, but the quick answer is that what you can do is that based on the errors, when you do your least squares and you're fitting to your data, the errors actually change the weight that you assign to any given data point. So errors are actually if you have uniform errors, if every point has the same error on it, then all of this stuff just works. If your errors are non-uniform, which is likely true, then you actually weight the points, and that changes it's a fairly simple fix. But yes, that's
Nick, before that, I think we need to explain what's the absolute, what's the relative error, what's the percentage error. I think that needs probably 5 to 10 minutes introduction to that. I'm happy to volunteer.
Okay, it seems like somebody needs to go into whatever the polling thingo is and put up errors.
Yeah,
so we can do this in two stages. One simple starting introduction to errors, just to understand the different type of errors and the way how that is applied and how to measure that experimentally in any sort of experiment. And then we can go into handling the errors in relations to curves or anything that Nick talked today. So it's 2 parts. In the first part, I'm a little bit afraid that not many of you understand the first part. Okay, I hope you understand what I suggested.
Yeah, no,
there are all sorts of different types of errors, experimental. Yep.
So when are you up, Miroslav?
Yeah, as I said, it's easy. This is what we teach in scientific literacy, more or less, that part. So I'm happy at some point to spend 10-15 minutes cut the slides for my lecture, and then I can explain the basics of the errors, introduction to errors. Then Nick, it's back to you.
I don't know about that.
Excellent. All right, thanks everyone.
All right.
Thank you for me too.